Hello, welcome again to Televison. This is our program on force and acceleration. In our last program, we studied motion without any forces. And we learned something rather important and fundamental about matter. Incidentally, in this program, in the last program, I talk all the time about forces on a body. What do I mean exactly by a body? Well, I mean a piece of matter. So we're talking therefore about matter. And by a body, I mean something like a block of wood that we used the last day, or maybe a billiard ball or a golf ball or something like that. But I might equally well mean a little particle so small that you couldn't see it, part of an atom, part of a nucleus, an electron, something like that. And this also is matter, and the laws that we find out for blocks of wood turn out to apply equally well to subatomic particles, and we can apply them in that region, though we must always be careful, of course, in physics when we go outside the region that we are familiar with. Well, now, what did we find out about matter the last day? We found that if you don't apply force, a push or a pull, to matter, then it either stays at rest or it moves on forever with constant speed in a straight line. And this is one of the crucial things. Motion doesn't require a force if it's uniform or constant speed in the same direction. The thing that characterizes force is change of the condition, from rest to motion, from steady speed to changing speed, or a change of direction. These are the things that are characteristic of force. And actually, this is a property of matter, just as important as the color of an apple or a flower. In fact, it's much more important because it's universal to all the kinds of matter we might ever discuss. And it's the property of what we might call sluggishness or stay-putness or something like that. And in fact, we give it a name. We call it inertia. So inertia is the thing we mean, the stay-putness of matter, the fact that it likes to travel at constant speed unless we act on it and do something to it. And that's why, of course, the first law of Newton is also called the law of inertia. Well, now, we saw not only the meaning of constant speed, but a sort of notation for describing constant speed, and we used rather nice techniques of multiple flash photography and hover disks and so on to study that kind of motion. Let's look at the photograph again, but this time it has been changed slightly. So let's see it here, and we should be able to put it into a little stand for you. There you go. It'll look a little better. Now there's our photograph, but this time we've put measurements on it, and those measurements were made simply by taking a meter stick and measuring along the photograph, which is arranged to be half scale. And now remember what this means. Here is the instant. At this instant, the light flashed, and we got an image on the photograph, and I call this arbitrarily, I might as well, why not, call it 0 time. And I also call it 0 distance. I say that puck, the dry ice puck, or the hover disk, hasn't moved at this point. Now, 1/10 of a second later, the disk has moved to here, and I measure that distance, and allowing for the fact that it's a half-scale photograph, I find 8.36. These numbers aren't terribly important, but because of the fact that they depend on just how hard I would push it, so let's not worry too much about them except to see them out here. Here, again, we have 0.2 of a second after the start. It has moved 16.64, and so on. And these are the distances which I measure off this. This is a real experiment. I measure these distances with a meter stick, and I get these values. Now we can see perhaps what I meant by delta x as well, because these, after all, are x running along here. X is the distance from the start, which is this first photograph. Delta x is the change in x. So I get my first delta x by subtracting 0 from 8.36, and there it is, delta x. I get my second delta x, the change in x, by subtracting 8.36 from 16.64, and I get this. And you can see all the values running along there that for my delta x's at different subsequent times. And you see what I mean when I say they're constant. I got 8.36, 8.38. Now, you may object to that. You say, well, 8.36 isn't exactly 8.38. But remember, this figure down here, these are centimeters, so these are tenths of a millimeter. These are quite small and easily mistakes in measurement. And besides that, of course, the hover disk isn't absolutely ideal. Maybe a slight amount of friction left. But we see that, in fact, the delta x's are constant. And when we divide those delta x's by 0.1, say we take this one here, we divide it by 0.1, we find that this measures the speed of the hover disk, delta x over delta t, to be 8.40 divided by 0.1, or 84.0 centimeters per second. And the constancy of that interval is what gives us which gives us constant speed. Now, there's another way in which we might approach problems like this. After all, the hover disk is a practical way of getting friction-free motion. The strobe light, or the multiple flash photography, is a very fancy way of measuring the time. We could have all sorts of other methods of measuring time. So let's not think that these are the only ways in which you can test the laws. There are plenty of other ways. In fact, we might imagine an experiment in which a man sits in a truck and throws out, has a little stopwatch in his hand, and every 0.2 of a second he throws out a bag of flour or something like that. And so as he moves along, his distance is marked out from equal distances in equal times. And most of our experiments that we discuss could be equally well visualized, not perhaps as real experiments, but we sometimes call them thought experiments, in which we use some ideal apparatus, which perhaps isn't entirely realizable, but which serves to make the point for us. But somehow or other, we get that table of x that I showed you, distance and time, and then we study it. And in the case of motion without force, we find that the delta x's, the changes in x, are constant for equal time intervals.